Hello, and welcome to the first video lesson on trigonometry. Let's break down the word trigonometry. This can technically be broken down into three Greek letters: tri, gonia, and metron. Tri in Greek means three. Gonia means corners or angles. And actually, together, these two words, tri and gonia, create the word trigonos, which in Greek means triangle. Which makes sense, right? It's a shape of three corners, and that's a triangle. And then the Greek word metron means measure. So together, you put all these words together and you get the measure of triangles. And that is exactly what trigonometry is. It is the study of triangles and their angles. Specifically, trigonometry mainly focuses on right triangles. Everything in trigonometry ends up referring back to a right triangle. Even when we deal with non-right triangles, there will be a way to relate them back to right triangles. So right triangles are really the essence of what trigonometry is all about, but we will get into that later. But first, in order to understand triangles, we need to understand what an angle is. So let's say that we have a ray. So a ray is basically a line segment that has a starting point. So this here is an example of a ray. It has a starting point right here, and then the line continues forever in this direction. So we put the arrow to represent that it continues going in that direction. Now we can also, let's say that we wanted to bring in a second ray. Okay, that is our second ray. Notice how I made the endpoint of the second ray at the same place as the endpoint of the first ray. Okay. The measure, or the figure that is formed between the two rays with a common endpoint, this common endpoint is called a vertex. The measure that's formed between the two rays, this here is called an angle. Now, normally to represent an angle, we use Greek letters. The most common ones that are used are the Greek letter theta. Also commonly used many times is alpha and beta. These two Greek letters are also used many times. Because if we're dealing with multiple different angles, we don't want to use the same letter each time. So these give us at least some options of other letters we can use to represent an angle. Now, sometimes the two rays may move. So if they share their endpoint, let's say that we have two rays. And let's take, for example, this one. And let's take, for example, this one here. Okay? Now, and then the angle between these two rays will be this. Let's say that this is angle theta. Okay? Now, sometimes the rays may move. Okay? Now, what we may do here is, let's say that we wanted to leave here the red ray static. We didn't want it to move. This is what we call the initial side. The initial side is a ray that does not move. So the initial side. And if we wanted to change the angle then, we'd then want to move the blue ray around. So if the blue ray is going to move counterclockwise or clockwise, this one's the one that's moving, and this is what we call the terminal side. And as the blue ray, the terminal side, moves around, the angle will be changing as well. This leads us into the most important type of way that we observe angles in trigonometry. And this is angles in standard position. So let's focus here on angles in standard position. So a rectangular coordinate, also called a Cartesian coordinate, they mean the same exact thing, is a coordinate system where you have an x-axis and a y-axis. This is a rectangular coordinate system. So, in order for an angle to be in standard position, the initial side, the side that does not move, has to be on the positive x-axis, with its initial side being on the origin, right here. So notice here how I put the initial side here on the positive x-axis. So it starts at the origin and continues going to the right. Okay. Now to be an angle, they have to share the same endpoint. So we'll say here that the terminal side will now be the one that rotates around. This is called the terminal side. Okay. Now notice here how the angle will be changing. This angle here is an angle in standard position, and from here on out we will only be talking about angles in standard position. So in future videos I will not be mentioning standard position, but let it be known that from now on angles will be standard position. Okay? So again, initial side does not move, terminal side does move. So of course the angle could change in many different ways. So let's say that the terminal side were here. If this was the terminal side, then this would be our angle. So the terminal side can move. Okay. Now, normally we deal with positive angles, but there is such a thing as negative angles. So when angles are in standard position, we can tell the difference between a positive and a negative angle. So, if the terminal side were to move in a counterclockwise direction, this angle here would be positive. This is a positive angle. So we start from an angle of 0, and then the angle starts getting bigger and bigger and bigger. However, if the terminal side now started moving in a clockwise direction, this angle right here would be a negative angle. So it starts from 0, the angle starts from 0, and the angle starts decreasing, or you could think of it as increasing but in the negative direction. So we go from 0 to -1 to -2, and so on and so forth. Okay? Now, how do we actually measure angles? So the most common way to measure an angle is with a special unit called degrees. So it has been standardized that if an angle is in standard position, here is our initial side, and then the terminal side were to rotate all the way around back. So it starts from the terminal side starts from the initial side and then rotates all the way around right back to the initial side. This angle here is 360 degrees, and we use the superscript up here to represent the degrees. Now this has nothing to do with degrees in temperature. This is just used to represent an angle. So why 360? Well, there are many debates as to where this number came from. I mean, that really could have been any number. Why would we choose 360? Well, it's been theorized that 360 is a highly divisible number. You can divide this in many different ways and get other whole numbers. Another place where the number 360 came from, which probably makes the most sense, is back in the ancient days before people were able to measure exact time and days. It was pretty much approximated that it took 360 days for the Earth to rotate around the sun, which is pretty much rounded to three. We now know that it's 365 days, but 360 was pretty close for the ancient people. So, and it makes sense, right? One full revolution, 360, right? So now knowing that, one full revolution would be 360. So if we wanted to get half a revolution, well, half of 360 is 180. So 1/2 of a revolution here would be 180 degrees. Okay. But then what about what's half of 180? Well, half of 180 is 90. So this quarter revolution is 90 degrees. And so on and so forth. Again, 360 is highly divisible. If we divide 90 again, and we get this here, this half of 90, that would be 45 degrees. And so on and so forth. So, in standard position, from here to here, this is 0 degrees because the terminal side hasn't moved. As it moves along, it goes to 90 degrees. As the terminal side continues moving, we go to 180 degrees. As it continues, we go to 270 degrees. And as it continues right back here, we go right back to 360 degrees as well. Okay? And this is if we are going in counterclockwise direction. However, now, remember how we talked about negative angles. What if the terminal side moved clockwise instead? So, if the terminal side now were to move in a clockwise direction, this angle here would actually be negative 90 degrees. From here to here, this would be negative 180 degrees. From here to here, if we're moving clockwise, we would go, this angle here would be negative 270 degrees. And then the final turn here, this would be negative 360 degrees. So knowing this, given any angle, we can actually easily determine the quadrant that that angle is in. So if you remember in rectangular coordinates, quadrant 1 is this quadrant here, the top right quadrant. Quadrant 2 is the top left quadrant. Quadrant 3 is the bottom left quadrant, and quadrant 4 is the bottom right quadrant. So think of it as creating a C shape, starting from quadrant 1 to quadrant 4. And this actually now makes sense thinking about angles, because as a terminal side rotates counterclockwise, we go from quadrant 1 to 2 to 3 to 4. So it makes sense. So now notice this, 0 to 90 is quadrant 1, but also negative 270 to negative 360 is also quadrant 1 if you're moving in a clockwise direction instead. 90 to 180 degrees, the terminal side would be in quadrant 2. And if we're moving in a clockwise direction, negative 180 to negative 270 is the range. Now again, if we're continuing further, if the terminal side continues moving, any angle between 180 and 270, the terminal side would lie in the third quadrant. And again, if we're moving clockwise, it would be negative 180 to negative 90. And finally, if the terminal side had any angle between 270 and 360, that angle would be in the fourth quadrant. Or again, moving in a clockwise direction, if the angle is between 0 and negative 90, the terminal side would be in the fourth quadrant. So let's do some quick practice here. Let's go ahead and draw this again. This is 0, 90, 180, 270, and then right back at 360 degrees. And if we were to move in a clockwise direction, we'd start at 0, then we'd go to negative 90, then to negative 180, then to negative 270, and then to negative 360. So let's think about this. Let's say that we were to have the angle 281 degrees. What quadrant would the terminal side be in? Well, 281 is an angle that's between 270 and 360. So that means that terminal side would have to be somewhere around here. So the terminal side would be in quadrant 4. Remember, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Let's take, for example, 27 degrees. Well, what quadrant would that be in? Well, 27 is an angle that's between 0 and 90 degrees. Therefore, that terminal side would have to be somewhere here in quadrant 1. So that angle there, 27, the terminal side would be lying in quadrant 1. Now let's take, for example, the angle negative 144 degrees. So again, you see a negative angle here. You just have to remember that a negative angle means that the terminal side is moving in a clockwise direction. It is moving in this direction. So negative 140 is a little bit greater than negative 90, or smaller if you're thinking in the negative direction. So it would be some angle that's between negative 90 and negative 180. Therefore, that would mean that the quadrant would have the terminal side would have to be somewhere in quadrant 3. And finally, let's take one more angle, for example. Let's say we had negative 3. So negative 3 here is an angle that's a little bit bigger, or again, smaller, if we're talking in the negative direction, than 0. So that means it moved 3 degrees in a clockwise direction. So that means the terminal side would be somewhere around here. So notice that the terminal side here would have ended up in quadrant 4 as well. Here I'm giving you 6 different angles in standard position. So if you remember, positive angles mean that the terminal side moves in a counterclockwise direction, whereas negative angles mean that the terminal side is moving in a clockwise direction. So your goal is to determine which quadrant the terminal side that corresponds to these angles is located in. So go ahead, pause this video and try to do these on your own. When you start the video again, the answers will show up in about 5 seconds. And there you have it. These are the quadrants that the terminal sides would be in. So continue practicing this, and this should become very easy to do. See you in the next video.